we're now recording. Okay, so if you navigate to the GitHub, under recommender, I added this file, basics, singular value decomposition, recommender system. Use that one, okay? So it's a more updated one, cleaner one. We'll go through it. Today, we're gonna review it and then think of the idea. So this should do some of the work that you need, okay, to be able to implement the recommender system. It's a more basic approach to it. But today I'll kind of review this in a way, and hopefully you guys will be able to use it. Okay, so let's go to the code here. And so you can see, I'm going to clean the kernel. Clear the kernel. Okay, so that should be clear now. Okay, so I'm just going to run it first, and then I'm going to describe it a little bit. But it's basically the code we had done before, just a version that should be simpler, hopefully. So first, I'm going to run this, right? And it provides some information about some of the movies. So just a high overview here. Then if we run, singular value decomposition, this is basically just doing a simple function here. We're going to explore another way of doing this today. So we run that, and then we've got our data. And then finally, we pick a movie. So I just picked, I think, a random number, 3000, because I didn't make a way of like viewing which movie it is and what their ID is, but you can do that. So let's say this is the matrix, right? So movie ID 3000. Then when I run the next step, the code now, the code now should list the movies that it's recommending. So this is linked now to the product, right? So we're going to play with this today. I don't know the reliability of it actually, right? So that's something that you will experiment in your homework assignment. But this should be a complete pipeline now. The weak link in this is probably this function here, cosine similarity, right? We can work on improving it, right? I believe there's a way to do that. And so at least I'm going to propose two ideas to do that. But do you guys see this? Does it make sense? All right, so you can download the code and just run it. So as I said, this is probably the version you should use because it prints out. So today what I'm going to do is, as I said, today is just a light discussion trying to get you to have this code working, right? So the homework assignment will basically be to try out, really to experiment that this works. You see that? And how do you experiment that this works? Find some movies, right? So find some comedies. It should predict other comedies. You can measure the performance. You can say, well, out of 20 movies that it predicted, yeah, I think 70% are comedies. Or maybe it says 20% are comedies, in which case that's a bad thing, right? And then pick another topic like action movies or sci-fi, just that's kind of one of the things. So tune it to make sure that it works, right? After you've tuned it to make sure that it works, then yeah, find another problem, advertisement, shoes, whatever you want to recommend, and run it on that. That should make sense, right? It should be pretty clear what you have to do. And that way you at least have a mechanism that you could implement to do recommendations. If you think about this, if you had a website, right, or something, all you had to do every night is download the database information of your clients and the ratings, and then you could run this code 2 a.m., a simple pipeline, and then every morning then you'd have recommendations for your customers, right? And then hopefully that will drive revenue. You can try different approaches, and then maybe over time you would find that it is working or it's not working. That's business, right? So that's kind of the idea there. All right, so anyway, so let's review the code here. just once again to kind of make sure we have everything. So, we imported NumPy and Pandas. We'll probably try an sklearn approach as well today to see if we can get that going. So basically we're using the movie lens database. So you can see that here. Okay. So we have the movie lens data. We read that from a CSV ratings, right? So read CSV data. Then we take data, user IDs, movie IDs, and we get the unique values of it. We can also do data head, right? Which just shows you a little bit of the data there. So then we want to read into the columns for ratings and the columns for movies into data ratings and data movies. We can also print the data movies head. And then we finally created a two-dimensional array ratings matrix, which, as we discussed in a previous lecture, that's just the number of movies to the number of users and their respective ratings. So we ran all this code, right? We ran all of this. And it should have given us this output here. So if you remember, we have here the data. We have about 100,000, I think it was, or something like that. User ID, the movie they rated, and the score they gave. Okay, so that was basically the idea. The movie IDs are here, and then the corresponding movie. And then here we have, for instance, for the movies, this is the head. So it has the genre, so fantasy, romance, comedy, and then we have other categories here for the movies. Okay, so that's basically our data, but we need to take it from being like this to being like this, right? And so we created that matrix. It's currently all zeros, initialized to all zeros, as some of them will be zero value. Then we said that the problem is that the movie IDs actually go from 1 to like 100,000, 170,000, but that would create too big of a matrix. So we have to create a mapping, right? So that is from the 170,000 mapping to the 9,700 unique movies, so that we don't have a sparse matrix. So here we grab from data ratings, we grab the values for rating, the values for movie ID, and the values for user ID. Then for movies and for users, we're going to create these dictionaries. For users, it is actually not necessary. I thought about maybe for simplicity next time, I will not do this one. But for completion, I guess I did both. So basically here, we create a movies dictionary, right, of the unique values. There's two dictionaries actually, and that's just so that it's easy to search for things. So one is from the reference ID to the real ID, and the other one is going to be from the real ID to the reference ID. So that's really all it is. Okay. So then we have here, we grab from movie IDs array, we grab all the unique values and save them in movies unique, right? Then we enumerate in movies, the movies unique arrays. So that's index and so this is movie. So this is the ID that it generates from 1 to 9,000, and then the actual ID that is in movies. Okay. And we're going to create the mapping. So here the IDX is 1 to 9,000, whereas the res is from 1 to 170,000 or whatever it is, right? And then we're just doing that mapping, and then here we just do the reverse. So is all this clear so far? Does this make sense? Are there any questions? All right. All of it making sense for the virtual world there in Zoom? Okay. So then we do the next one. For users, exact same process basically. So I'm not going to repeat it, literally the same thing. All right. So far, I'm kind of just reviewing, as I said today. My goal today is only to wrap up this topic, right? And so that you guys can do the assignment. So once we have that, the next thing is now we need to populate the array with we have the dictionary, so we can go ahead and populate. The matrix will be called ratings matrix, right? That's that line. So it is here, ratings matrix dot shape. Okay. So then we have a simple for loop here for I in range of length of ratings array, because it's every single rating that we have in there. We want to populate. Okay. So what we do there is, because the three lists are aligned, right? So we have 100,000 entries where we have the user, the movie ID, and the rating itself. So we just need to iterate through one of the arrays. They have the same lengths and they match up. So then we use this as an index, and then now we can grab from user IDs array and from movie IDs array the user and the movie. So we have now, for every iteration, we grab one user, one movie, one rating. Okay, so now that we have the real ones, we need to get the reference ones, right? Because we're going to actually populate this with the reference ones. So then from dictionary users, uniques, dictionary real reference, we grab the real value and we get the reference. And the same for movies, right? We're going to get from the real, the reference, right? And so now everything is mapped to those ranges of 1 to 9,000 and 1 to 610. So we've got these, we use these two as indices here. We use these two as indices, and then we just plug in the actual rating, and boom, our matrix is done, right? We've got our matrix created. Is this clear, guys, so far? Right, so remember, that's the 9,000 by, that's the 9,000 by 610. It says, run this. And you can see here's a slice of it, just so that we can take a look at it. You can see that still it's mostly zeros, right? And this is us being efficient. So imagine if we had been really inefficient, it would have been mostly zeros and it would have been huge. Right? So I hope that's pretty clear for you guys. Once we have that matrix, the movies by user with the ratings inside, we're pretty much ready to just do the singular value decomposition. We've also talked about this in the previous lecture. So where we discussed the methodology. So if you remember, all we need to do is know that when we applied singular value decomposition to this matrix, it's going to decompose it into 3 matrices, right? And you can give them any name that you want. When we run this, it's going to give us it should give us, I think it's just thinking, yeah. So it's calculating these values, and then notice it created a matrix that is 9,700 by 9,700, one that is 610 by 610, and then 610 values. You guys see that? All right, remember what's important now to consider is the following. So that for this, I guess we should go to the whiteboard. So the next part that's really important to understand So the part that's really important to understand is that when, we have that initial matrix, right? The initial matrix ratings. But then we're going to apply singular value decomposition to it, and that's going to give us, I'm just using the math notation here, which is the one I remember, B, right? So it gives us these three matrices. We could put, a comma here. Now, what's important is if, let's say the movies one, right? So we can go by the indices here. If I share screen, right? We can see that the U is the one that is 97 by 97. So that's the movies basically, right? Map to the movies. So now what we want to do is notice that it created a matrix. Notice that it created a matrix that is 9,700 by 9,700 approximately. Every single one of these rows is a movie. So movie 1, movie 2, ... movie 9,700, right? So, but it created, if you remember, it created 9,700 of these, which are the concepts. So these are concepts, right? The idea is that it locked on to, for instance, sci-fi, romance. This example is intuitive, so we should be able to understand that it is locking on to these examples. All right, so what's important here, though, is that this is equivalent to having features, right? Like these are the features that we had before. So you can think of it as F1, F2, F3, all the way to 9,700. If you remember in one of the homework assignments, the WECA one, you had to do something called feature. What was it? What was the name of that? Feature what? Ranking. Yeah, feature ranking, if you remember. You guys had to rank the features, and then you had this idea that you may not need all features, right? Here, singular value decomposition has created these concepts, 9,700 of them, which are exactly the same idea. They are features with the only additional information, and they're also kind of ranked for you already. But it inferred these new ones based on an algorithm, right? So now it inferred this, and so these are the most important. So you can think of it as this is more important than this one. So really what you can do is if you have 9,700, you really don't need all of them, right? You only need a few. And so you can basically slice out a few columns to make it smaller. So now, for instance, you could end up with a matrix. So you could take that original U, which is 9,700 by 9,700, and turn it into a U that is 9,700, but with a reduced amount called N, whatever you want it to be. So for instance, you could say 100, and that may be good enough. You can play with this value, and there's like algorithmic ways of figuring out, this cutoff, but we don't need to get to that, You can just think, the way that you can think of it is, because the more you cut off, let's say, the more you not use this, you are losing some information. That's for sure, right? There might be a little bit of data. So as you cut more and more, you're losing some data. So what I would recommend is whatever your computing power is, efficiently, use that. Do you see what I'm saying? Like if the algorithm could say that 50 is enough, but if your computer handles 150 at the same time, at the same metrics, pretty much just use 100, right? Because you are losing every column that you take out may have some meaning. It's like saying romance, sci-fi, comedy, rom-com, documentary about sci-fi that had some comedy. You know what I mean? So that's a more difficult one. Yet it could have been useful for that one person that really just liked that. You see that? So that would have been the feature that for this one movie, that's like an artsy, film, from Europe, but had all those themes. There might be someone else that liked it, and they would have been found on that column. So there might be some value, but for the majority of the people, so what I would say is just use whatever your computing power supports. Computers are pretty powerful today when it comes to like 100, 200 features. So we don't have to worry so much about, finding the optimal point. So really, that's why I recommended just doing this. This is called feature compression as opposed to feature ranking. So this is a perfect, for the second exam, this is a perfect question, right? What's the difference between feature ranking and feature compression? Okay, so make sure you understand this concept. But like I said, feature ranking is the way that we did it with the WECA examples, and singular value decomposition is the example that we do it with compression, okay? Remember, in feature ranking, the features were just dropped. Whereas here, we don't use the original features, the ratings, right, from the users. We use a converted set, okay? The components. Is this concept clear for everyone? Or that, yeah, go ahead. Yeah. Yeah, it's the both of them. Because it's a good question, actually, because singular value decomposition gives you the 9,700 components, right? But you have to slice out a few to compress it. So it created 9,000. You just don't have to use all 9,000. As I said, the intuition is science, romance, this, and then artsy French movies that have romance, science, and sci-fi in them. So that column over here could have been useful for like 3 users in all of Netflix. I don't know. So your accuracy would drop by that little percentage because that would have been useful. But for the rest of the people, all the other ones were. So compression is the combination of singular value decomposition that creates the components and then just slicing up a few of them. And remember, we start from the left to the right, because that's the way that it puts them. Do you guys see this? This is an important concept. Feature ranking with WECA was, we have the 98 pixels from an image, 784 pixels from an image. We're going to drop some based on the feature ranking. And then we end up maybe with 300. We just drop them, but we keep the original ones. Here, we don't use the original ones that were movies to users, right? Instead, we created the components as we discussed in the lecture, and then we just slice out a few. Is this clear for everyone? Questions? This is the most important concept, and you might see in like the calendar, et cetera, that it said compression, but really if you understood recommender system, compression is just this little bit. Because you don't always, you can use that technique for everything. Just whenever you have really large data, you can always apply this, always. Right? Any data set that you have. In fact, the theorem, if you remember, said, given a matrix that is m by n, you always have singular value decomposition. So if we have singular value decomposition, that means that we can take the original data and compress it every time. This is very common. A lot of people do this whenever you have high dimensional data. Let's say you have a data set and it's got like 10 dimensions, right? You can't visualize this. It's not possible. But if you apply PCA to it or singular value decomposition to it, you can create a matrix that is 10 by 10. We know that the first 3 are the most important, right? So we slice those out. Guess what? Now we have a space of size 3 for all the samples. So what can we do here? We can plot it. in 3D. So basically, we're compressing a large space, an infinite space, into this smaller space. Is this perfect? No. Remember what I said. Information was lost here. This info is gone. You see that? What's the analogy intuitively? What's the analogy for this? Well, the best analogy I can give you for this is basically a shadow. So you guys see me, right? But then the camera sees me, but then you have another camera there. If you shine a light on, start here, you shine a light on me, see my shadow, correct? Can you still say things about me by my shadow? Yeah, right? Especially if you have a whole bunch of people and then you're now seeing their shadows, you can say things. You know who is taller, who is shorter, right? And so that's basically this. It's almost like a shadow of the original data, but sometimes that shadow for your problem might be good enough. If you're making a system that detects how tall people are, the shadow is just as good as the original color 3D high definition image. Got it? So that's the important concept to understand. So that's really the intuition today. Everything else is just code. So are there any questions? No? All right, so let's go back to the code then. Not hearing any questions here from anyone. Okay, so we go back to this. So we generated the singular value decomposition here, US and V. And then now the goal basically is to recommend things, okay? To recommend things. So let me actually do this kind of in parts. I'm gonna move this. Yeah. All right, so this is where we are. And then let me just now update this. Okay. So now that so the first part was to get US and V, right? So we've got them. The next part is, I'm going to just kind of skip the cosine function for now. We'll come back to it. But it's this part, right? So in this part, what we want is, I say 50. This 50 is basically the value here, right? So this, the 50 here that I'm going to slice out or whatever, or 100, right? So it's the number of components that I'm selecting out of the total data. Okay, that's that 50 there. And so I select that I want 50 principal components. Then you're going to have to select the movie ID, right? You can iterate through the dictionary or through, you can iterate through, for instance, where do we have the movies? The thing is we have movies that are, we have, let's say, movie, right? So we need ref to reel. Ref to reel. So I'm going to go over here. We need a movie. So we've got ref to reel. Okay. And ref to reel gives me, let's say I pick 3,000. So actually I'm going to do it. Right, so I pick a movie. This is the ref movie ID, reference movie ID. So then I'm just going to plug that in here, ref movie ID. And what should this give me? This should give me the real movie ID, correct? Right. So that's one way of doing it. Actually, a better way might be to, what's a better way of doing this? I want to see the movies, right? So I want to see. From data movies, let's see if I can just print out four-line data movies print line. Let me just try that. Okay, that didn't work. Wait, where are the movies? The movies are in. It's in data movies. Okay, so let's do it like this. Pandas frame. Data movies. Data movies ID equals something. Let's just see. Let's just pick something. Okay, what's the indentation? Why is this not doing it? So this is, yeah, so this is the one. It's not being intended. Well, anyway, I'm gonna pick one of these. So what's one category here? Toy Story? What is that? Like cartoon, I guess. All right, so the movie ID is one, right? So let's go with that one. So the movie ID is one, Toy Story. The real ID is one, which is for Toy Story. Okay, so I have that movie. Now, that's the movie that I'm going to compare to all the other movies. Do you guys see that? So that's the basic idea. So to do that, though, I need to convert it to the equivalent. I need to use the dictionary, right? So the real to ref. So this is real to ref for movies. So this should give me ref movie. Right. So all I have to do here is in movies uniques dictionary real to ref, I have to plug in real ID. And I should probably call it real. Toy Story. Movie. You guys understand? So that's the basic idea. Are there any questions so far? All right, so now we're going to pass. So there's a question. Okay. Yeah, so as I said, so far all we've done is we read the data in, created the dictionaries, and we created the matrix, right? We populated the matrix, then we did singular value decomposition. So all of this is done. Okay. And now we want to compute the similarity. And what that means is it's basically like KNN in a way. It's the same idea. So now I'm going to go over here and we're going to do something like what we did with KNN. Do you guys remember the Euclidean distance? You literally could use the Euclidean distance for this. There's no reason why you can't. It's exactly the same thing. So if you think about it, what we've done here is we took the original 9,720, 9,720, right? That's the U. We sliced it. So U, not sure why I made that so big. And then from here to 50, right? So we slice 50 or 100 columns, however many you want. And that gives you the slice version. So let's call it slice U. But now you have basically all the movies, right? So you have all the movies here, 9,720, represented as vectors of size 50 or whatever size you want. I just picked the movie ID 1, right? Toy Story. And what am I going to do now? If you think about it, this is a vector space of size 50, right? There's 50 vectors in that space. And so now I just throw in the movie Toy Story, right? And I'm going to compare it to all the other movies. You see that? And then I find the most similar ones. So literally, you can do this with Euclidean distance, just like we did in KNN, the exact same thing. So basically, we compare this one to all the other ones, all 9,720 minus 1. Okay, so we compare it to all of them. That's exactly the step that's happening. As it turns out, there is a function. We have our options are 1 or 2 Euclidean distance, but people have found out that it is better actually to use something called the cosine similarity. Okay, cosine similarity. They have found that this is a better approach to use, but it's the same idea. It still relies on comparing, one vector, 1 by 50, to all the other vectors, which are size 50, but there's 9,000 of them. So we still do a type of a distance metric. And this is a distance metric. It just so happens it's called the cosine distance. Got it? Is this concept clear? Because this is important, right? And so this is where, if we go back to the code here, that's where this function comes in, top cosine similarity. This is the function where you're going to do that. So if you think about it here, what I'm doing is I slice the matrix, right? So I grab the original U over here of the singular value decomposition. I grab the original U. Oh, here. I grab the original U. I grab all the rows, but only the columns from the beginning until K, where I've defined K to be 50. And you can define it to be whatever you want. And then this slice matrix will be one of the inputs to this function. So you provide the slice matrix, the movie ID, which is going to correspond to one of the rows of slice matrix, and that you want the top 10 closest movies or most similar based on this cosine similarity. This will return top indices, which basically means it returns the IDs of the movies. But remember, it returns the reference IDs. We still need to map them out to the real IDs. Got it? All right, so that's the idea there. So we would run that. And so the last part is just once we have the reference IDs, then print out the movies, right? But first, before we do that, let's go to the cosine function. So you can see here, I'm going to modify this. I'm going to clean it up a little. Clean this up a little. All right, so the goal here, okay, so a function to calculate the cosine similarity, and then it sorts by most similar and returns the top n. This is similar to the Euclidean distance. Right, so this is similar to the Euclidean distance function, right? But just a little bit different. So we'll talk a little bit about the theory behind it. It's just a formula, really. This is, so here you can see, basically, we know that this is the data, right? All of the data already sliced. This is the movie ID, and this is the top n. So the first thing we need is, if you notice, movie ID here. I mean, I literally can just say movie ID here and get rid of that line. Right, and so we can get rid of this line of code. Okay. So this, notice that I said the dimension is 1 by 50 because I just sliced out one of the vectors for that movie in that space, and I'm going to compare it to all the other ones. Okay, then here, this is really where the magic happens. This is actually being done with NumPy. This just means the dot product. So, oops, sorry, I didn't mean to do that. All right, np dot dot. So that's the dot product. And that's basically a way in linear algebra to be able to perform multiplications. So here, for instance, you know, it's a way that you mathematically multiply a vector times a vector times a matrix, etc. Right? So here, you know, we have this vector, and then we have that vector. And let's say, just a simple example, A, B, C, D, E, F, G, H, I. So you'll take this times this, and it'll give you one value. And this times this, and it'll give you another value. Do you see that? Intuitively, then, we're going to end up, if this is size n, this is going to be size n. With the distances inside, and then the distances might look like 7, 3, 5, 10. So then what we want to do is we want to rank them, right, in ascending order. So the smallest, because they're the closest at the front, and then we just select the smallest ones, the top 10 smallest ones, and then we'll have the IDs. And that's it. So that's kind of what we're doing here. Okay, so Go back to the code. Okay, so the function then, notice it grabs the one row from that, a 1 by 150, and then it's called movie rows. So then we just perform that multiplication that I just described, np dot dot, and it's gonna be movie row, right? That's that vector times the whole data. And then we just do this transpose so that the things align. So we just, that's basically all that happens. So this changes the shapes of it so that we can understand the dimensions. So if you guys want to look at the shapes, we could do that. Say print, and then you could say movie row dot shape, and then we could say data dot. Well, actually, let's do print data dot shape, and then we can do print. Actually, let's do data transpose going to be equal to data dot t, right? And then print data transpose. Okay, so if I run that, and then I run the other ones, should have printed out. So these are the shapes, right? So if you notice, 50 is the size of the vector. You guys see that? And then the original data was 97450. So it's kind of like this, right? And then now it is 50 by 974. Do you see that? So we kind of flipped it like that. The 50s are now here in this, right? And it allows you then to do the multiplication because it needs to do, if we don't do the transpose, it would try to multiply the vector of size 50 with the things that are of size 9724. By flipping it, now it knows, okay, no, it's this vector of 50 times the vectors of 50. Does that make sense? Questions about that? That's really just like, it's a math trick. But sometimes, that's why there's a bit, to avoid knowing all the math, because there's actually, I'm going to show you another way of trying to do it. And we can just abstract this concept, okay? But I just want you to be aware that that's really what's happening there. I'm going to I'm going to comment out these, I guess. Yeah, go ahead, please. Yes. Yes. So data.t is transposing itself to whatever the first parameter is. That's right. We need to do that, we need to know like the alignment. So no matter if it should, in this case, it could be a matrix too. Yes. The trick is this, that we need to know, we need to get the alignment of them correctly. That's a trick. That's one of the things that you do kind of manually when you get to this low level in like machine learning. So you'll do, for instance, so think of it this way. So I have 1, 3, 2, 7. That's a vector, right? And I want to multiply it, right? Times, but I might have something like this. Oops, sorry, that's too big. It's 4, right? So there's only 4. So 7, 3, 1, 5, 2, 7, 5, 2, ... 1, 7, 1, 0, something like that, right? So what you want to do is you want to do, let's say this times that, this times that, this times that. You see that? But you can't right now because they don't have the right dimension. And so that's why you transposing just means flipping it so that we do, so, you know, this times that is what it's trying to do right now. This times that. It doesn't work because the dimensions don't align. When you do the transpose of it, actually, I'm going to. When you do the transpose of it, you keep, let's say we keep this dimension like that. For it to work, we have to flip it so that it is, you know, kind of like this. So now, you know, I'm just making up numbers. Dot, dot, dot. You see? So now what happens? I can do it now because this times that, 4 to 4. Do you see that? This times that, 4 to 4. I can do that computation. The computation is simple. It's just, if we look at the first 3 values, the first 2 vectors, it's this vector times that vector. So the computation is 1 times 7 plus 3 times 1 plus 2 times 2 plus 7 times 0. You see that? That's it. That's what we're doing. So this is 7. This is 3. 2 plus 2 is 4. That's 0. So then that's 14. That's the result. So for every one of these, we end up with a value. And so that's the distance. Got it? Yeah, exactly that. This is obviously the Euclidean had like a squaring and a square root, if you remember that. So this is a different function called the cosine similarity, where you just do this multiplication and then divide by something called a norm. Normalization of this data. But so that makes it better. But I wanted to keep it simple, right? So I wanted to keep it simple, and then we're going to try this with a function in sklearn, which so that we don't have to write it out like that. So basically, but basically this is the idea of it. Okay, so we have, by doing this, we end up now with a vector not of size 9,000 by 50, but 9,000 by 1. We just have a distance for every single one of the values, and that's the similarity of it. You guys understand? And then once we have the similarities here, once we have the similarities, what we do, the next step is to take that vector of values and sort it with a function in NumPy called arcsort, which what's really handy about that function is that it's going to sort them by the values. Like imagine it's going to rearrange them, but it returns the indices. And that's really nice. It's really neat because it takes a lot of coding work out of doing that. In the past, without that function, you had to think of all that logic. You no longer have to think about all that logic. Okay, so for instance, what arcsort does is, let's say that I have the values like this. So I have a vector. So this is 7. These are the distances, right? So 3, 80, 1, 4, 0, right? But the indices of it are 0, 1, 2, 3, 4, 5, right? Which correspond to the movies. Remember, it corresponds. These are the movie IDs because we calculated the distances on what? On the 9,720 by 50. Remember this? So really, every one of these was a movie. So these are the movie IDs, the reference IDs at least. Is this concept clear? Guys, questions? Okay, so then now I want the movie IDs, but I want them sorted. So the closest one to that movie was 0, right? So I'm gonna sort it. So it's gonna be 0. I'm gonna actually use the same color. So it's gonna be 0, 1, 3, 4. That's 0, 1, 780. That's how you sort it, correct? That's the sorting of it. But it will return the indices, the original indices. That's what argsort np.argsort will do for us. So this will be then 0 is 5, 1 is 3, 3 is 1, 4 is 4, 7 is 0, 80 is 2. So these are the indices of the movies. Let's say we just want the top 3. That's your answer. We found now the 3 closest movies to the original one. You guys understand? Questions? All right, so that's what it's doing there. So if we take a look over here, that's what this is doing. It returns the sorted indices. And now, notice now this shows all the indices. So then we again slice it from beginning to top end. So I think it's like the top 20. So now that's what is returned. So we've got the top 20 movies. And now we're just going to go ahead, and that's what this gives us. And that's what's printed out here. So if I run this here is the IDs of the closest movies to Toy Story, right? That's what it should be. And then now I'm going to run this code. And according to this, the closest movies to Toy Story are The Gift, The Shawshank Redemption, Highlander, Clockwork Orange, The Untouchables, Lost in Translation, One Flew Over the Cuckoo's Nest, Rounders, Shrek 2, Forrest Gump, and Monsters. What would you guys say? Toy Story, right? Yeah. Monsters, Inc., yes, and Shrek 2, I think, are cartoon movies. But yeah, so that's the idea. And so where is the problem? Okay, so let's say that this doesn't work, and we'll go over this code in a second. But where might the problem be? The problem might be then, because singular value decomposition, there's nothing more we can do with it. That's done. So there's no more improvement. But if I was to say, okay, I need to improve something, then I'm going to go here to this function. Because as it turns out, this is not the optimal similarity. This is not actually the cosine similarity. Okay, so I'm going to now show you that. So what is the cosine similarity, right? So let's talk a little bit about that, because that's really where we might find some improvement, hopefully. I don't know. Maybe it won't make a difference, but assuming everything else in our code is correct, and we'll check that last part in a second. But the cosine similarity is a metric used to determine how similar two entities are, irrespective of their size, right? So kind of what I explained. Mathematically, it measures the cosine of the angle between two vectors projected in a multidimensional space. So the idea is that instead of measuring like the distance between 2 points, it's going to treat the vectors like that, and then it measures an angle. Do you see that? So this is kind of the math behind it, the intuition of it. So in the vector space, you can represent those points as vectors, and then now, you measure the distance between, and that measures how similar they are. And it has been found that it works. So when we say two vectors, they could be two product descriptions and anything, just arrays of data. The actual formula for this is, so let's say cosine, it's going to be the vector A times the vector B. This is actually what we implemented so far. I have that NP dot, that's the vector times, just instead of just putting in vector to vector, you can put in the whole matrix, it'll do it. It doesn't care if it's 1 or 100 or a million, right? It just does the multiplication and it'll return the size of whatever the largest one is. As long as they are transposed correctly, it'll do it. Got it? The additional component is that there's a denominator component called a norm. So you have to find, this is a multiplication, so you have to do that part as well. The norm of it. The norm of a vector, basically, if we go back, translates basically to the the length of the vector. You can think of it that way. It normalizes by the length of the vectors themselves. So every operation that it performs vector-wise is going to take that vector and normalize. Okay, so that's the idea there. So usually that translates to, if you want to think of it, of how that might be. So the norm of a vector, let's say you have a vector A, B, and C. So the norm of the vector would just be the square root of A squared plus B squared plus C squared. It's a metric that allows you, as I said, to calculate a type of a magnitude of that vector. Okay. So, but yeah, I don't want to get into all that, all those details, right? We can just use the function without knowing all the details of it. And so we can try to apply a function called the cosine similarity. Okay, so let's try that one. And maybe that one will be better because that cosine similarity, unlike mine, does not include it should include everything, should be optimized. Here, though, if you're interested in implementing this in detail, you would have to calculate the I think it's called a norm, and probably NP norm of each vector and get the answer. You see that? So it should be like NP norm of movie row times NP norm of the data D. Do you see that? Like that. So that's kind of the missing part. But instead of it, this is going to start getting too complex, too much detail. So instead, what I want to try out is something called the sklearn framework, which we have used already. So from sklearn, we are going to import metrics. So from sklearn dot metrics dot pairwise, we are going to import cosine similarity. You guys see that? So basically, instead of writing it all out, we can maybe just implement a function for it. And there's a lot of these, by the way. So there's a lot of versions that we can use for this. I'm going to save it. Oh, yeah. Sorry. I always do this all the time. From sklearn metrics pairwise, import cosine similarity. All right, so I'm going to run this now. Okay, we had sklearn before, so no errors, right? So that's good. And we run the singular value decomposition. So everything seems to be good. Okay, so now here we would need to change this similarity to the other one, right? So that's the goal here. Cosine similarity should be similarity cosine similarity. Oh. and we input the parameters. So in this case, it should be movie row, comma, data. And let's see if we need to do the transpose. It may be that it does the transpose for you. It checks the dimensions and it does it. Otherwise, we'll do it. So this time around, let's save it. Okay, this is where it would give us an error. Okay, it gave us an error. Reshape your data either using arrays, reshape if your data has a single feature, it contains a single sample. So I think hopefully expected 2D got a 1D instead. Okay, so let me see if I can. These are NumPy arrays. Well, let me actually just make sure they are. Okay, so try to. That still gave the error, right? So slice data is definitely. I'll make sure. Yes, I'm going to make sure again. Still gives the error. So the last thing I'm going to try then is to do data dot transpose, right? See if I get those. See that the problem that I'm not getting the dimensions correctly, and it doesn't like. So it's definitely that. I mean, I'm hoping this will fix it, but. No, it's still. Reshape your data either using. Let me take a look at the dimensions. Movie row and data. There's oh, and it's, I'm going to put these before the error. Oh, there they are. So it's 50. So it's 974 by 50. And that's data, right? But it's flipped. I think the problem is this one. It's not like that. So I did the transpose here now. 50 by 97. And maybe this one needs to be 1 by 50. So maybe this needs to be 1 by 50. It's just not liking that. So to do that, gonna be really low. Let me try that. On squeeze. So attribute on squeeze. Okay. Okay. Let me just look up that error then. So the error is reshape your data either using array reshape. Oh yeah, okay, maybe it's actually telling me how to do it. Right? This is, I think if I just do this. Try that. Okay, let me change the transpose part. It should work with a matrix. It should work with a matrix. I'm just not getting the dimensions correctly, I think. So it says incompatible dimension of X and Y matrices. X dot shape 1 equal 1, while Y shape 1 equal 50. But that's how I had it initially. So I made it 50 by 1, right? You can see that 50 by 1. I had it and this is 50. So this should be, yeah, this is where you spend a lot of time sometimes. So 50 by 9, 724. I think that's correct. So then I need, if this is 50, the logic is that like this, right? So then this one should be not 50 down, but 150, which is what I'm trying to do. Yeah, so this should be 50 here. All right, let me try. Huh. Worked this time, didn't it? Nope. One hash. Oh, but this is another problem. So this is actually because I made the things NumPy arrays instead of lists. So that's another issue. But this worked actually this time around. It calculated, you can see them here. It calculated the things, the IDs. So the problem was, if you notice, it's a good classic problem. Getting the dimensions can be a little bit painful, as you saw. If I go back to the whiteboard here, my problem was, so my data was like this, right? So 700 by 50. And then this vector, I don't know what it was, probably like that, 50. This is 1, right? But it didn't like this. So what it wanted was, so that it can do the computation, it wanted this to be 1 by 50, and then this one, oops, $50 by 9,720. So that, as I said before, it could take something of size 50 and multiply it by something of size 50. Then the next one, something of size 50 multiplied by something of size 50 all the way to the end. Do you guys see that? Does this make sense? So when I did the transpose of this data, it gives me that, no problem. But then this wasn't in the right dimension. So what I had to do was, I ended up telling it that I needed the column part to be 50. And what, by writing -1, I just say figure out the other one. Because there's only one here, it'll figure it out to 1. And this is how I was able to get it to work. The unsqueeze function that I was trying only works in something called TensorFlow and PyTorch. I was hoping NumPy would have an equivalent, but maybe I used it incorrectly, and that's why I was doing that. So, but reshape worked out, -1, 50. I believe that's actually what I wrote in the code. Yeah, you can see that, -1, 50. So now I know for sure the columns is 50. So it's called a row vector as opposed to a column vector. You see at the -1, it just figures out that the value should be 1. And so then it has the dimensions correctly there. And then now it can do the similarity. And hopefully this similarity is better than the other one that we had used, just a dot product, because it's got the norms and everything. You guys understand? So you can use either this one, you could use the Euclidean distance, or you can use this cosine similarity from sklearn. This gives you the similarity, and then after that, I do the NP-arc sorts and the top n. So that is returned down here, but it gave me another error then that says, so I ran this one, right? I ran this one, that worked. It gives me these indices. And then now here, when I run this one, it gave an error because I did change. So it doesn't like that it's a NumPy array. But the only thing that it's receiving here is, it's receiving, where do we call it? Yeah, top indices, right? So top indices. Oh, I think this is the thing it doesn't like. Yeah, I think so. Okay, so we'll have to fix that. So let's take a look at this code, the last part of it. The movie ID was what? The movie ID was, where did we have that? Was 1, right? But I just want to know if it was the real or, so movie ID was 1, the real, and then we went from real to ref. Okay, so we've got 1 is the movie. So then over here we need to tell it movies unique, dictionary, reference to real. What do I need? I need, oh, but I know the real one, don't I? It's 1, Toy Story, correct? Okay, so then I don't need these. I just want to print out the name. This should print out Toy Story. So my real movie ID is 1. Real movie ID is 1. So this part should return not the GIF, but Toy Story. So let's do that. There it is. Works, right? So we've got Toy Story there. So then here is the problem. If you look, this returned a NumPy array, and I'm iterating through it as if it's a list, right? So let me see if I just do top indices 0. Let's see if that'll fix it. Okay, so why is it printing out all these? All right, so now what do I want to do? So I grab the indices, these 1660, all these. How many did I return? Just 20, right? Top 10 actually. 1, 2, 3. Did I? Should only be. We should print out the shape of this. The size. So print length top indices, right? Let's see what that gives. Why is it giving me so many moves? I'm going to comment these now. One. Yeah, no, I get that. Let's actually, you're right. Let's take a look at this one. The sorted indices. If this worked, let's print out shape of that. Suspicious here. Let's take a look at similarity actually, because this 1 by 9, 7, 24. That should be correct, right? Because it's the all 9,724 movies. So then why didn't it? See, this is the similarity. Then this should have sorted them. And then just return the top 10. Do you guys see that? This is where there's some kind of a problem. Oh, this sorted indices. Okay, yeah, this would be 9,724 too. It's really print here. What I need to print is this one. Dot shape. I need to know that this is only about 10 or 20. No, it's not. Sorted indices and similarity. I want to see if it's sorting. Yeah. So yeah, so the values change, right? This one has like the real values of the data, and then this one seems to have the indices. So that's good. So it did it. So that's good, in my opinion. But the sorting is not working. Sort indices, and this might be that this is for a list. Let me make that into. Let me make that the sorted indices into a list. Okay. So then this hopefully. Okay. Try it again. And I'm going to just before I print the indices, I'm going to print the shape for length. So it should be 10 or 20, right? Okay, so we do this again. Size is one. Yeah, this I think the problem is what is the problem? Trying to make this into a list. I don't get why that list size is not. List size 1. Okay. Yeah, I'm gonna have to work on this. It's almost done, but this part, I don't know why. So what I'll do is I'll post this code on the GitHub, and then you guys can access it. It's just this part is missing. Because this, I was hoping this function would be better, similarity. And I just don't see. Why it's not converting. Okay, there we go. So you see it's giving me a size of 10 now. Do you guys see that? Okay, so now it's a list. So if I run this, top indices. Oh, that's because I had done this. There's 10 of them, right? If I do print ref, yeah. So these are the IDs, okay? And then now I need to length top indices. Okay, so now print now recommended movies. Okay. Okay, so it's these. So now these should be ref IDs, correct? Not the real ones. So I need to get the real ones. So print ref, so then movies uniques ref to real. Yeah, that gives me real movie ID. Oh, and then I need to then print the real ID and print that movie. Okay, there we go. So now it says that closest movies to Toy Story are Untouchables, Rocky IV, Videodrome, Tron, Bronson, Romeo and Juliet, Too Late, Villain, Highlander, Rounders. What do you guys think? If we tried the other method, change some of the code. Okay, so this is, these go together here. So this is similarity and P dots. So if we just use this method, I think it was just NP dots. Sort indices, np.arg sort. Similarity, right? Hopefully this will work. Yeah, and this one gave us Shrek, Monsters, Inc. So which one of those do you think works better? NP dot, right? So it seems to be. So basically, yeah, I expected this one to be a lot better actually, but it wasn't. So it seems you can try both methods. Some suggestions for improvement could be, one thing that might help is instead of 50, 200. Just increase the number of vectors. So let's try that. I'm going to try it with NP and with, so you guys see what I did here, right? This is the method with just NP dot, and this is the method with the sklearn approach, right? So just comment or uncomment one or the other. So I increased the size to 200. Let's see if that solves it, and we'll wrap up with that. What about here? Toy Story recommended, To Kill a Mockingbird, Office Space, Lock, Stock, Barrels, Clerks, Life is Beautiful, Shine, Royal Tenenbaums, City of God. Probably not. Right, so comment this out by this method. I think I just have this duplicated. Do you guys remember if this had been like that? Do you remember that? I know movie rows we corrected. It was 1 by 50. The T. So why did I delete? I'll have to recheck this again. It's a new class. So I'll check it out again, see what I got wrong, and I'll post this code. But as you can see, it's got two methods there, and basically to get better results, we can play with the dimensions. We tried two functions. We may also try the Euclidean distance. It may just be that that's the limit of it, right? And it's not recommending very well. But that's the procedure. So we'll stop here for today and we'll continue on Monday. I will post this as soon as I get it all fixed up. Yeah, I'll create one. Yeah, I wanted to get this code ready to go, and the results just don't seem to be so great, but I'll take a look at it and I'll post it. All right. But we should be, it was working. I just don't know why now. I messed up something when I did the change. All right. So we'll stop here for today and I'll see you guys Monday.
Could you help me fix an error I have in my code? I have
let's go to my office and we'll do it there because I have to. Can you wait? Lenny?
Yeah.
All right. So
when's your office hours today?
I'll just go now. I'm gonna walk to my office. There's a new class coming in.
I'm actually at home right now, but I can come to school. It's no big.
No, you don't have to come to school. Just via this Zoom thing.
Oh, okay, cool. Thank you.
Stay there. I'm gonna go to my office.
Thank you, Professor.
Yeah. Yeah. I just had like a bunch of pictures and files. Can I resubmit those in a Word document to you? Yeah, just email it. Okay.
And I think maybe the problem with that is since it's going up with ratings, maybe it's just grouping well received from the users. Like the characteristics, I'm sure are part of it, but it might just be that like some of the research better received in general.
Yeah, I'll have to look. I mean, we've tried two functions and you know, neither one, I guess we're expecting too much and this is the method. So I'll have to double check, but too bad the dimensions just, you know, messed up a little. I'll fix that. Hopefully it should be a minor thing. And then we'll wrap, I want to wrap this up. I had hoped today, but we'll wrap it up on Monday. Yep. Yep. Lenny, are you still there? Guys,
Yes.
other people on Zoom, you can leave. We're done with class unless you have questions. Stop the recording.